Hey, what's up, guys? Last section that we're doing in the book, section 8.3, regular Markov chains. And we're only going to do part of this section. We won't really actually get into the ones that are called regular Markov chains. We may get to that after the final, but it's not covered on the final, so we'll just kind of see how it goes. So anyway, up here at the top, just some kind of refreshed on what we found out so far this chapter. So each row of a Markov chain is a probability vector. In other words, it's a vector, so one row. In the row, it all adds to 1, okay? And then k-step transition matrix. So if I want 2 transitions, it'd be p to the second power, and so on, okay? So just thinking about going from state to state, we started out, basically we've been telling you what state it's currently in. All right, well, now we want to look at what are called initial state vectors, which essentially gives us a chance of it starting in a certain state, and then we use that along with the transition matrix to find what the probability of it ending in a certain state is. So if we look down at the first example down here, number 1, so we've got 3 states. It says the probability that the system is in state 1 is 0.3, probability it's in state 2 is 0.2, probability it's in state 3 is 0.5, and it says write the initial state vector for the situation. So a vector, remember, is a matrix with just, we're talking about a row vector here. So we're just a matrix with one row. We've got our 3 states, 1, 2, and 3. All right, all we do is put our probabilities in. Okay, so state 1 is 0.3. Okay, right there. Probability of state 2 is 0.2. And then probability of state 3 is 0.5. That's an initial state vector. Easy as that. Okay. Moving on. We're going to use that here a bit more. Okay, so get rid of that. Okay, so now we've got a state vector, calling it x for a 3-state Markov chain. So now we're figuring out the state vector a little bit differently here. It says it's equally likely to be in state 1 as state 3, 5 times as likely to be in state 2 as state 1. So this is kind of technique we talked about first semester with probability when we're given situations like one is the same, equally likely as this, the other one is 4 times or 3 times as likely, whatever. So 1 and 3 are the same. So these, we can write these as fractions. Okay, and then it says it's 5 times as likely to be in state 2 as state 1. So if 1 and 3, they're the same, we just call those 1. State 2 is 5 times as likely, so put that as a 5. So if I want to figure my denominator out, all have to obviously be the same denominator. These have to add to 1. Okay, so 1, 5, and 1 add to 7, so that means these are all over 7. Okay, 1/7, 5/7, 1/7. There's my state vector. Okay. All right, so now we use this problem, I forget which section now, 8.2, I believe. So it says volume of beverages sold at a restaurant fluctuate from day to day. If the volume sold is high today, then tomorrow will be high with a probability of 0.6. If it's low today, it'll be low tomorrow with probability of 0.3. So my transition matrix, which we'll call P, okay, and I'll use high as my first state. So if it starts out as high, probability of being high again the next day is 0.6, so 0.6 right there. That means low would be, because these have to add to 1, so 0.4. Oh, no. Get my pen back. Okay. Then it says if it's low today, low tomorrow is 0.3, so just be careful where you're writing it. So from low to low, the 0.3 is down here. And again, they have to add to 1, so that's 0.7. All right, so we're going to use that here in a little bit, in part B, actually. So part A, so right above part A, okay, talks about our state vector. It says the owner of the restaurant estimates the volume is 3 times as likely to be high as it is to be low today. So my state vector, which is going to get a little more official here. We're going to call that x sub 0. So I just have two states, high and low. So 3 times is likely to be high as low. So if high was the first one. So it's a 3-to-1 ratio. So 3 plus 1 is 4. So 3/4 and 1/4. Okay. And I'm going to put those as decimals. Just it's going to be a little easier to make these calculations if they're decimals. At least in a calculator. All right, but it really doesn't matter. All right, so there's my state vector. So here's where we use this. Part B, using the estimate as the initial state vector, find the probability of high volume 2 days from now. Okay, so here's basically what we're going to be doing. Okay, if x sub 0 is right now, x sub 1 would be tomorrow, x sub 2 would be 2 days from now. Okay, so to find this, all we do is I take my state vector, x sub 0, and we multiply. So I need to do 2 transitions. Think back, all right, in 8.2 when we did 2 transitions, we multiplied p by itself. We did p squared. So this is going to be x sub 0 times p squared. Okay, so all I end up doing is I find p squared. Okay, p was right up here. Okay, my star very poorly there. Okay, there's p. We just multiply that by itself and then multiply that by this state vector. Okay, I'm going to do that on the next slide where I've got some room. All right, part C. All right, now it's asking, and let me go back real quick. In B, it says find the probability that it's high 2 days from now. So what's going to happen when I multiply the state vector x sub 0 times p squared, you're going to get another vector, okay, and it's going to just be a vector like this, and you just have to remember which was first. So I've got high and low. All right, so what my answer is, since I want to know what's probably being high, I'm just looking for whatever that number right there is. Okay. In C, what we would do, so now we want 3 days, so that's x sub 3 is what we call that. So that's my initial state vector times p to, well, what do you think? Third power. Okay, and then that's again going to give me just another row vector here. Okay, again, because you're going to, you'll see why when we actually do the multiplication here, but we're going to do p to the third power, multiply that by, sorry about my dog barking in the background. He goes crazy anytime anybody gets near my house. So we're going to do p cubed, all right, whatever that is, we multiply our state vector times it, and we get another row vector, but now I'm looking probability that it's low, so it's going to be whatever's in that spot. Okay, and that's really all we're going to be doing in this lesson today. 3 days from now, so we're finding this. All right, so again, you just do p times p times p, and it ends up being kind of a lengthy calculation. And you would just multiply that by x sub 0 to get your state vector. And it's going to just be another vector. We would just look for the second number for the most part. So I'm going to do B here just to show you how that works out. Okay, so we were doing, write down what we were doing again here, x sub 0 times p squared. So first thing you got to do, find p squared. Okay, so that was p times p, which if you remember, p was this. Okay, so we'll multiply that by itself. Okay, so 0.6 times 0.6 is 0.36. 0.4 times 0.7 is 0.28. Add those together, that's 0.64. Okay, remember, we don't have to do this next calculation because we know they've got to add to 1, so that's 0.36. Okay, so as long as you get the first one, the second one you can do easily. So just make sure that first calculation is correct. Okay, next one, 0.7 times 0.6 is 0.42. 0.3 times 0.7, 0.21. So we add those together and you get 0.63. Again, they add to 1, so 0.63 plus 0.37 is what's going to add to 1. So there's my p squared. Okay, remember what we're doing now. We need to take our state vector times p squared. So my state vector again was 0.75, 0.25. Okay, and we multiply that by the p squared. Didn't leave myself a lot of room here, but you get the point. Okay, so, and then it's just, again, row by column. So we take our 0.75 and 0.25 times this column. So 0.75 times 0.64 plus 0.25 times 0.63. Okay, feel free to use a calculator for this. You end up with 0.6375. All right, again, they've got to add the 1, the other spot. What we're doing is 0.75, 0.25 times the 0.36 and 0.37. But since our row vector that we're about to get has to add to 1, we just take 1 minus 0.6375, which gives me 0.3625. Okay, so that is x sub 2, which is what we're trying to find. Remember, high was first, low was second. Okay, we want to know what's the probability that it's high 2 days from now, 0.6375. Okay. So the next one is asking x sub 0. Basically, it's our, if I go back to it real quick and take a look. Okay, p squared would be 2 days. Okay, we don't really have to use a state vector for that problem because I'm basically going from low to low. Remember what we've learned, low to low would be 0.37. So right there, 2 days go by, and that. So anyway, okay, this next problem, okay, says, so back to that same example, volume today is low. How many days must go by before the probability of low volume is greater than 0.35? Well, really, if we just go back, we are greater than 0.35. Okay, one more thing to talk about. Okay, and this is kind of the same deal. So I'm gonna have one more thing at the end here, though, just to kind of some helpful equations. So bear with me through this one. I don't necessarily need to work through this whole problem for you. Just kind of show you the setup, and then if you want to work it, you can, but not really necessary. We've got our three-state vector. There's three-state Markov chain here. We've got my state vector, initial state vector. We've got my transition matrix. I want the probability that it'll be in state 2 after 2 transitions. So 2 transitions, so x sub 2. Okay, so since we have a state vector, we just take our x sub 0 times p squared. Okay, and remember this is p. So for this one, a little more tedious. You have to multiply p by itself. Okay, you end up with 3 by 3. Okay, if you do that, just so you can see, p squared is, if I can read my original writing when I worked this out, 0.15, 0.52, 0.33, and then 0.10, 0.22, 0.08, 0.7. Okay. And then I'm just taking my state vector times that. Okay. And the state vector again is the x sub 0. So I would do the 0.2, 0.3, 0.5 times this. You end up with 0.14, 0.444, and 0.416. Okay. Probably it's in state 2, right there. 0.444 or 44.4%, however you want to write it or say it. Okay. Well, state 3 would be 0.416. Okay. So this kind of leads to, so the regular Markov chains are basically, we multiply this out, our entries are basically non-negative. Okay, so in other words, when I say multiply it out, when I multiply out the transition matrix, like do it to the p squared, p cubed, p to the 4th, p to the 5th, p to the 12th, p to the 50th, we don't get negatives. And then what ends up happening when what we really are into in this section is looking at long run behavior, where we would be you look at it and you do it after a certain amount of transitions. It all ends up all the outcomes. So all of these start to center in on the same thing, or at least on each row is the same basically. Not something we're going to have time to get into. I don't think. If we do, great. If not, I don't think you guys will necessarily, you won't miss it. But it is some interesting stuff to take a look at. It's just the second half of section 8. Question here, same deal. It's asking probability that it is in state 3. So last thing, just a couple things to write down. Make sure you have. So if we're given an initial state vector, so first two sections we weren't given the state vector, okay? Now we're given the initial state vector. We're not, so in other words, remember first two sections I said, hey, we're in state 2, what's probability of going to state 4 or whatever. Now we don't know what we're currently in. We have that initial state vector which gives me probabilities of starting somewhere, okay? So probability of being in a certain state after 2 transitions, okay, that's these formulas I was writing. So we call it x sub 2. So it's my x sub 0, my state vector, times p squared. Okay. 3 transitions, x sub 0 times p cubed. 4 transitions, x sub 0 times p to the 4th. Okay. So that's that. You can have a pretty short homework assignment for today, which I think you can probably bang out pretty quick. So anyway, let me know if you have any questions. Have a good one.